Dear students, myself Kiran MP. I am working as assistant professor in the Department of Computer Science and Engineering in Government Engineering College, Kushalnagar. I welcome all of you for this session on container loading problems and the pigeonhole principle. Let me a look at agenda of this session. At first, let me have a discussion about container loading problems. Here, first I'll state you with a problem statement of what actually container loading problems means. And then there are three different cases of solving container loading problems. We will have a detailed discussion about all those three cases. Once we become familiar with container loading problems, we will have a discussion about an interesting topic known the pigeonhole principle. Now, coming to container loading problems. See here, you will be given some m distinct objects, m different objects, m unique objects, and you will be given n containers. There are two cases. Containers may be distinct or containers may be identical. Okay, I repeat. You are given m distinct, m unique objects and n containers. Containers may be distinct or may be identical. The problem is filling this m distinct objects among these n containers. Okay. Containers, as I said, may be distinct or may be identical. Okay. Means, and you will be asked to fill those objects among these containers with none container empty. A container might be left empty. So I mean to say, you will be asked to determine the number of ways that exist for filling this m distinct objects among n containers. Okay. So coming to case 1. In first case, as I said, objects, all m objects are distinct. I mean all m objects are unique. And in the first case, even the containers are distinct. Okay, I mean all containers also distinct. Now, the objective of case 1 is to determine the number of ways that exist in filling these m distinct objects among these n distinct containers with none of the container left empty. I repeat, the objective of case 1 is to determine the number of ways that exist to fill these m distinct objects among these n distinct containers with none of the container left empty. So, when we analyze this, okay, it resembles like onto functions. Okay, when we analyze this filling of m distinct objects among n distinct containers with none container left empty, it resembles onto functions from a set with m objects to a set with n containers. Got it? So, to determine the number of ways of filling these m distinct objects among these n distinct containers with none container left empty, we need to determine the number of onto functions that are possible. And we know number of onto functions that are possible from a set A with m elements to a set B with n elements is given by summation k equals 0 to n minus 1 to the power k into n minus k into n minus k power m. And this is the solution for case 1. I mean the number of ways of filling m distinct objects among n distinct containers with none container left empty is nothing but number of onto functions that are possible from a set consisting m objects to a set consisting n containers. Now case 2. See here, the objects what we are given are distinct. Means m distinct objects are given. But the n containers which are given are identical. Means there is no differentiation among the containers. Okay. So I repeat, the given m objects are distinct, whereas given n containers are identical. Now, the objective of case 2 is to determine the number of ways of filling these m distinct objects among n identical containers with none container left empty. I repeat, the objective of case 2 is to determine the number of ways of filling m distinct objects among n identical containers with none container left empty. After analyzing, we see the solution is nothing but the Stirling number of the second kind, which is nothing but the number of onto functions from a set with m elements to a set with n elements divided by n factorial, and it is denoted as S of m comma n. So the solution for case 2 is Stirling number of the second kind, S of m comma n, that is number of onto functions from a set with n elements to a set with n elements divided by n factorial. That's nothing but summation k equal to 0 to n minus 1 power k into nc n minus k into n minus k whole power m divided by n factorial. The third case is you're given m distinct objects, you're given n identical containers, and here the objective is you need to fill m distinct objects among n identical containers, but here the container might be left empty. I repeat, the objective of case 3 is to fill m distinct objects among n identical containers with empty containers allowed. So, what actually total n containers are there, right? So, first case, I can leave one container empty. Got it? The second case, I can leave two containers empty. The third, I can leave three containers empty. In general, I can leave n minus 1 containers empty. Okay, when I leave n minus 1 containers empty means, okay, when I leave n minus 1 containers empty means all m distinct objects are placed into one container. Into one container. So actually, to be more precise, the summation of case 3 could have been written as summation I equals 1 to n minus, 1 to n, that's right, 1 to n. So see, means the first case is that, listen, what the object states, you need to fill m distinct objects among n identical containers with empty containers allowed. So the first choice is that I'm going to place all m distinct objects into single container. So how many ways exist, I need to determine. The second case is that I'm going to fill all m distinct objects into two containers. So I need to determine how many ways exist. Similarly, at the last, I'm going to fill all m distinct objects into n container, all n containers. So how many ways exist, we need to determine. So sum of all these ways is nothing but a final solution. Let us have a look at an example of container loading problems. So just have a look at example 1. Here, set A, which consists 4 elements, A, B, C, D, represents 4 distinct objects, and set B, which consists 3 elements, 1, 2, 3, represents 3 distinguishable containers. I repeat, a set A consisting 4 elements represents 4 distinct objects, and set B consisting 3 elements represents 3 distinguishable containers. Okay, I mean, in general, there are 4 distinct objects and 3 distinct containers. And the question is that, in how many ways can these 4 distinct objects be distributed into these 3 distinguishable containers with none container left empty? I repeat the question. In how many ways you can distribute 4 distinct objects among 3 distinguishable containers with none container left empty? So we are very clear, it's nothing but number of onto functions that are possible from a set with 4 elements to a set with 3 elements. So substituting m equals 4, n equals 3 in the summation, we are going to get answer as 36. So there are 36 onto functions. That means there are 36 ways of distributing these 4 distinct objects among 3 distinct containers with none container left empty. Let us have a look at example 2. Here, set A consists 4 elements A, B, C, D, represents 4 distinct objects, and set B consists 3 elements 1, 2, 3. In this case, assume this represents 3 identical containers. I mean to say you are given 4 distinct objects, 3 identical containers. Now the question is that in how many ways can these 4 distinct objects be distributed into these 3 identical containers with none container left empty? I repeat the question. In how many ways you can distribute 4 distinct objects into 3 identical containers with none container left empty? We are very clear, right? The solution is Stirling number of the second kind. That is, we have to compute number of onto functions from a set with 4 elements to a set with 3 elements, and that should be divided by n factorial. Is it? So substitute m equals 4, n equals 3 for an expression s of f comma n. Okay, then we are going to get answer to be 36 by 3 factorial. That's nothing but 6. So 6 ways to distribute 4 distinct objects among 3 identical containers with none container left empty. Clear? So now, let me have a look at one more example for case 3 of container loading problems. Now, set A consists 4 elements A, B, C, D, which represents 4 distinct objects. Set B consists 3 elements 1, 2, 3, which represents 3 identical containers. I repeat, set A consists 4 elements A, B, C, D, representing 4 distinct objects. And set B consists of 3 elements 1, 2, 3, representing 3 identical containers. Now the question is, in how many ways can these 4 distinct objects be distributed into 3 identical containers with empty containers allowed? I repeat, the question is, in how many ways can these 4 distinct objects be distributed among 3 identical containers with empty containers allowed? So, what may be the solution? See, the first case is that let me distribute all 4 distinct objects into one container. Let me distribute all 4 distinct objects into one container. That is nothing but S of 4, 1. I mean, S of 4, 1, there are two identical containers left empty. And the next choice is, let me distribute 4 distinct objects among 2 identical containers by allowing one container empty. That is S of 4, 2. And the third choice is that, let me distribute all 4 distinct objects among 3 identical containers with none leaving empty. I repeat, first I will distribute 4 distinct objects among one container by allowing 2 containers empty. Second choice is, I will distribute 4 distinct objects among 2 identical containers by leaving one container empty. And the third choice is that I will distribute 4 distinct objects among all 3 containers with none leaving empty. So they are represented as S of 4, 1, S of 4, 2, S of 4, 3. When I sum this, I am going to get 14. So there are 14 ways of distributing four distinct objects among three identical containers with empty containers allowed. So till now we have discussed what is container loading problem and what are the three cases of container loading problems, and also we have solved one example for each cases. Now we'll proceed with an important interesting topic, what is known as the pigeonhole principle. See, it states that if there are m pigeons and n pigeonholes, I repeat, there are m pigeons and n pigeonholes, and number of pigeons greater than number of pigeonholes. Number of pigeons greater than number of pigeonholes. Then two or more pigeons occupy the same pigeonhole. Then two or more pigeons occupy the same pigeonholes. It means, let me tell you, when number of pigeons are more than the number of pigeonholes, okay, then at least in one of the pigeonhole there may be two or more pigeons. Got it? Or let me repeat. If number of pigeons are greater than the number of pigeonholes, then at least one pigeonhole, okay, at least one pigeonhole will have two or more pigeons. Got it? So, in general, okay, there's some, in this principle, there's one formula. Let me tell you that formula, as you can see on the slide. P equals, okay, floor function of m minus 1 by n plus 1. Here, m is number of pigeons, n is number of pigeonholes. Okay, and what this formula means, when number of pigeons greater than number of pigeonholes, okay, then in any one of the pigeonhole, what is the minimum number of pigeons? What is the minimum number of pigeons that will reside? That is P. Okay, let me tell you, if m is number of pigeons greater than number of pigeonholes, that is n, then if this formula gives, that is the value of P, is nothing but the minimum number of pigeons that we can find in any of the pigeonhole. Okay, so let me review or restate it. Okay, see here, what actually pigeonhole principle states that if number of pigeons are greater than number of pigeonholes, then at least one of the pigeonhole will have two or more pigeons. See, in some cases, what is the minimum number of pigeons that will be residing in any of the pigeonhole? We need to determine. Okay, in some cases, we need to determine the minimum number of pigeons that will be in any of the pigeonhole. I repeat, I need to determine the minimum number of pigeons in any of the pigeonhole. And for that we have formula P equals m minus 1 divided by n plus 1. Now let me see your analytical skill. Okay, let me see your analytical skill. See here, In an office, there are 13 file clerks or 13 employees out there. Okay, there are 13 employees. So the question here is you need to tell me the minimum number of file clerks or minimum number of employees to have birthdays during the same month. Okay, let me tell you. In an office, there are 13 employees. In an office, there are 13 employees. And my question to you is, what's the minimum number of employees to have birthdays during the same month? What is the minimum number of employees to have birthdays during the same month? So, when you analyze, okay, the first employee might be born in Jan, the second employee might be born in Feb, third employee in March, the 12th employee may be in December. Okay, if I assume the first 12 employees might have born in unique month, okay, then what about the 13th employee? He should have born in the month in which one of the 12 employees have already born, right? I repeat, assuming first employee should have born in Jan, second employee should have born in Feb, and the 12th employee should have born in December, then 13th employee should have born in one of the month in which already one of the 12 employees have born. So, I mean, here the birth month of employees, I can treat it as pigeons. I repeat, the birth months of employees, I can treat it as pigeons. And the month name, Jan, Feb, March, April up to December, I can treat it as pigeonholes. Got it? So the number of birth months we have is 13. And the number of pigeonholes we have is 12. So to determine minimum number of employees to have birthdays during the same month, we use that formula. P equals the flow function of m minus 1 divided by n plus 1. On substituting m to 13 and n to 12, we are going to get this value as 2. So it's very clear, at least two employees of 13 employees should have born in same month. Clear? I repeat, at least two clerks of 13 clerks should have born in same month. Let me have a look at one more problem. What it states? It states that there are 10 red marbles, 10 white marbles, 10 blue marbles. So totally how many marbles? 30 marbles. It's given there are 10 red marbles, 10 white marbles, 10 blue marbles. So totally 30 marbles. And we draw one marble at a time. Then the question is, the question is to determine minimum how many marbles to be drawn to have 4 marbles of same color. Let me repeat question. There are 10 red, 10 white, 10 blue marbles. So altogether 30 marbles. Okay. And we are going to draw one marble at a time. The question is to determine what should be the minimum number of drawing a marble, so that I'll get 4 marbles of same color. Got it? So rather than using formula, let me analyze in general. Okay. Let me say first draw, it might lead to red. Second draw, it might lead to white. Third, I may get blue. Okay. First draw, I have obtained red. Second draw, I have obtained white. Third, I have obtained blue. Fourth, again red. Fifth, white. Sixth, 10. Sixth, blue. So till now, I have two marbles of red, white, and blue. Now seventh, again it resulted in red marble. Eighth, it's resulted in white marble. Ninth, it resulted in blue marble. Okay. Now after drawing 9 times, I have got 3 marbles of each color. So in the 10th draw, I may get one of the marble, that is red, white or blue. Okay. In the 10th draw, I may get a marble which is one of the color red, white, blue. And prior to that draw, I mean from in the previous 9 draws, okay, I have got 3 I have got 3 marbles. I have got 3 marbles of same color. So in the 10th draw, I got one more marble of the same color. So the minimum number of draw is 10. Is it? So that I will get 4 marbles of same color. Now let me apply this to pigeonhole principle expression. Your M is nothing but pigeons, right? That's nothing but number of marbles. Total marbles are 30. So they represent 30 pigeons. And the colors red, white, blue, they represent pigeonholes. So that is 3. Got it? Then substituting M 30 to M and 3 to N in expression, I'll get P to be 10. So it means to say minimum 10 marbles should be drawn to a 4 marbles of same color. So the pigeonhole principle is quite interesting, is it? So let me wind up this session. Thank you for listening.